A great deal has already been said about the most famous super heavy tank project in history. Its staggering weight, potential capabilities, and obvious shortcomings have long been thoroughly analyzed. However, today we will try to understand how such a controversial machine actually managed to find its embodiment in metal. Friends, meet the Maus, the German super heavy tank that became the ultimate symbol of World War II Gigantomania. How did the analytical and pragmatic Germans decide to create a 188-ton monster that physically could not cross a single bridge? Why, in the midst of a severe crisis at the front, did the country's leadership continue to spend scarce resources on a project that was clearly doomed to fail? Today, we will examine in detail how this contradictory machine made its way from blueprints to real prototypes. Be sure to watch this episode to the very end. You will learn how the pursuit of a preposterous vengeance weapon slowed down Germany's mass production achievements, and what actually happened when this steel giant ended up on the testing grounds. Let us begin. In the spring of 1943, in one of the halls of the German military headquarters in East Prussia, stood a strange structure. It was as tall as a 3-story house and 10 meters long. It was made not of steel, but of wood and plywood. Yet its dimensions precisely replicated those of the future combat vehicle. The wooden mock-up certainly did not weigh 200 tons. However, for those who built it, weight was not what mattered. What mattered was the silhouette, the angular, heavy, looming hull, with a turret that seemed the size of a small house all by itself. This mock-up was not brought here for the engineers. It was brought for one specific man. The leadership of Germany had long harbored a weakness for everything that was the biggest, most powerful, and most impressive. When the wooden copy of the future tank appeared in the hall, the effect was exactly what the presenters had hoped for. It is difficult to say what had a stronger impact, the sheer proportions of the machine, or the absolute confidence with which the engineers spoke of its capabilities. Nevertheless, the decision was made almost immediately. The project was given the green light. On paper, everything looked logical. A tank capable of withstanding almost any existing shell. A tank whose armor made it invulnerable from the front at any reasonable combat distance. A machine that was supposed to turn the tide of battle by its appearance alone. Yet, there was one detail that no one in the headquarters hall voiced out loud. A wooden mock-up could be assembled in a few weeks by a carpentry workshop. Turning those proportions into combat-grade steel, finding metal of the necessary thickness, designing components capable of supporting the machine's own weight, and building an engine of suitable power was an entirely different task. It would not take a few weeks, it would take nearly 2 years. The first running prototype would not appear until the end of 1944, when Germany's position would be vastly different from what it was in the spring of '43. When that moment arrived, it would turn out that many of the problems that seemed minor at the wooden mock-up stage had evolved into something far more serious. But first things first. Before discussing the finished machine, we need to understand who was behind this project in the first place. Who took on the audacity, or perhaps the recklessness, to turn a wooden toy into one of the most expensive and controversial tanks in history? This person was not a random choice. By the early 1940s, Ferdinand Porsche was not just an engineer. He was a man whose name the German leadership uttered with particular trust. By that point, he had decades of development experience behind him. From early electric vehicles to production cars that already bore his name. He knew how to talk to the decision makers at the top. More importantly for this story, he rarely said no to them. That is precisely why, when the topic of a super heavy tank arose, the choice fell on him. The project received the working designation Type 205. Later, another name would stick to the machine, Maus, which translates to mouse. The name was chosen to be intentionally ironic, to mislead those who might catch wind of the project ahead of time. Porsche undertook the work with an enthusiasm that was hard to miss. However, there was one episode that explains a great deal about the nature of this enthusiasm. From time to time, Porsche prepared special reports for the leadership. In them, he reported that the opposing side was allegedly also developing super heavy tanks of comparable size. These tanks did not exist, not a single one of them. There was also no intelligence data confirming such projects. On the other hand, these reports worked perfectly as arguments. If the enemy was building something similar, then Germany could not afford to fall behind. This meant that resources for the Type 205 had to be allocated without delay. The loop closed in on itself, and the very man who was personally interested in the continuation of the project was the one closing it. Later, Armaments Minister Albert Speer recalled this episode quite directly. According to him, Porsche took on this venture in an attempt to please the leadership. Even then, it was clear that a machine weighing 200 tons could only be built in single units, rather than a production run capable of influencing the course of events. Speer understood this. Guderian, the Inspector General of Armored Troops, understood this as well. Yet their voices on this particular matter proved weaker than the leadership's personal trust in one designer and his regular reports about dangers that did not exist. Under this artificial pressure, the project received genuine, real priority. However, dreaming up a tank on paper and drawing an impressive wooden mock-up was the easy part of the story. It proved much harder to take these ambitions and translate them into concrete figures, into millimeters of armor, tons of mass, and horsepower of an engine that did not yet even exist in reality. When these figures were put on paper, it became clear that this machine went far beyond anything built before. The finished vehicle received the official designation PZ-KPFW-8, making it the 8th in the line of armored combat vehicles of this family. Behind this dry index, however, lay numbers that are worth analyzing individually, because together they are simply hard to fathom. The length of the hull was 10 meters. For comparison, that is the length of 2 passenger cars parked bumper to bumper without any gap. The width was nearly 4 meters. The tank physically could not fit on a standard road without spilling over the shoulders. But the key figure was the mass, 207 tons. To understand what this means, let us compare it to the heaviest production tank of that period, the PZ-KPFW-6 Tiger Aus B, also known as the King Tiger. This was a machine that was considered a heavyweight of its time in its own right. Well, the new tank turned out to be 50% heavier than the King Tiger. Not 5, not 15, but an additional half of the Tiger's own mass on top. Translating 207 tons into a more relatable image, it is roughly the weight of 35 adult blue whales, the largest animals on the planet, placed side by side on a single steel platform. Here, the first logical question arises. Where did such a mass come from? A tank is not just an arbitrary block of steel. Every ton in it serves a purpose. In the case of this machine, almost the entire mass was directed toward one specific area: protection. This tank was built on a principle that can be summarized in a single phrase. It is better if it doesn't arrive, as long as it definitely cannot be penetrated. This sounds logical in theory, yet behind this logic lay a chain of engineering compromises, each pulling the next one along. Thicker armor meant a heavier hull. A heavier hull required a more powerful engine. A more powerful engine demanded more fuel and more space to house it. More space meant the mass increased yet again. It was a vicious circle from which the engineers could not escape. They simply kept increasing every parameter until they ended up with a machine that, in terms of size, resembled a small building rather than a piece of military hardware. This armor, which caused all the other problems, deserves a separate discussion. The numbers involved are capable of surprising even those well acquainted with the military hardware of that era. The upper glacis plate of the hull had a thickness of 200 millimeters, 20 centimeters of steel, set at an angle of 35 degrees from the vertical. This angle was not an aesthetic choice or a minor detail. A projectile hitting an angled surface must travel through more metal than if the plate were standing straight. Additionally, at a favorable angle, a shell might simply ricochet off without penetrating at all. 20 centimeters at an angle worked as a much greater effective thickness than the same plate placed vertically. The sides of the hull were protected by plates 180 millimeters thick. The rear was 160 millimeters. Even the weakest point of this hull exceeded the frontal armor of most tanks of that time in thickness. However, the turret set the true record. The front of the turret was 240 millimeters, 24 centimeters of solid steel. The sides and rear of the turret were 200 millimeters on each side. In other words, the turret of this machine was protected almost equally from all directions, which was quite rare for tanks of that period, where the sides were traditionally made significantly thinner than the frontal projection. To visualize this in practice rather than just in numbers, a hit from most existing anti-tank guns of the time at a frontal distance did not guarantee penetration of this armor at all. The vehicle was indeed protected at a level unattainable for other production tanks. But here we must pause and ask a simple question. At what cost was this invulnerability achieved? Every centimeter of steel is weight. The more centimeters there are, the more mass there is that must be moved, driven down roads, and transported across rivers and bridges. The designers built a virtually impenetrable fortress. However, fortresses are not known for their mobility. In this contradiction between invulnerability and mobility lay the main problem of the entire project, a problem that would become obvious a bit later when it came to logistics. Before that, however, it is worth looking at how this armored fortress was supposed to return enemy fire, because the armament of this machine proved to be no less unusual than its protection. For the main gun, the engineers chose an existing system rather than a new development, a 128mm gun. The same weapon system had been installed shortly before on the Jagdtiger tank destroyer, a heavy self-propelled gun based on the same vehicle family. The decision was pragmatic. Anti-aircraft and heavy guns of this nature were designed to project high muzzle velocity, which meant excellent ballistics. For a tank gun, these qualities meant the ability to penetrate enemy armor from a great distance. The distance here was indeed impressive. Aimed fire with this gun could be conducted from a distance of 2 kilometers. At that range, the weapon guaranteed the defeat of the vast majority of tanks existing at the time, regardless of which side they presented to the shooter. The most interesting design decision, however, was made not in the primary caliber, but in the secondary armament. Traditionally, heavy tanks received machine guns to fight infantry and light vehicles at close range. Here, they decided otherwise. Instead of machine guns, they installed a 75mm gun paired coaxially with the main gun in the turret. A second such weapon was planned for installation separately as an anti-aircraft measure for protection against aerial attacks. This created a situation that looks almost comical on paper. A machine whose primary purpose was to suppress enemy tanks at long range was additionally armed with another full-scale gun instead of a standard machine gun. In terms of firepower, this tank surpassed many self-propelled artillery units of the time that were considered specialized tank destroyers. Here, a question naturally arises. Why would such an elephantine machine, which could barely move, need a gun capable of hitting a target 2 kilometers away? The answer to this question is far more sobering than it seems at first glance. A firing range of 2,000 meters only makes sense if the tank can reach a favorable position and hold it. Yet for a machine weighing 207 tons, problems with doing so arose from the very beginning, and the cause was not the gun, but the mechanism tasked with moving it. To make such a mass move at all, an engine was required the likes of which no one had built before. Moving a hull weighing 207 tons was a task for which no ordinary automotive or even tank engine of that era existed. Therefore, the designers had to develop a power plant virtually from scratch. This was undertaken by engineer Joseph Kays of the Porsche company. The resulting engine had a displacement of 44.5 liters. For comparison, this is about 20 times the engine displacement of a typical passenger car of that period. The output was 1,080 horsepower. This engine was built not at Porsche's own facilities, but on the production lines of the Daimler-Benz company, where equipment capable of handling such a large unit was available. On paper, 1,080 horsepower sounds impressive. For comparison, the King Tiger, which we already mentioned as the heaviest production tank of the period, had an engine that produced about 700 horsepower for a machine with nearly half the mass. It would seem the calculation was logical, greater mass required more power, and the engineers provided that power. However, here is the result obtained in practice. The final maximum speed of the vehicle was only 20 kilometers per hour. 20 kilometers per hour is a speed at which a trained person can run a short distance. On a highway, a cyclist could easily overtake this machine without much effort. On rough terrain, the speed dropped even further, where it was measured in just a few kilometers per hour. The result was a machine with power that on paper surpassed the metrics of any other production tank of the era, but in practice, this power was spent almost entirely on simply moving its own weight. The engine had virtually no reserve left for speed, maneuverability, or rapid repositioning. The massive motor was ready. The colossal mass could theoretically move. Yet a problem arose that no one seemed to have seriously thought through to the end during the design and calculation stage. How was this machine to be transported to where it was supposed to be deployed? 207 tons was not just a problem for the engine, it was also a problem for the entire road and bridge infrastructure of the time. Not a single existing bridge in Europe was designed for a load of that level. Most bridges were engineered to support tens of tons, with a maximum capacity for vehicles weighing 70 to 80 tons. A machine weighing more than twice that would simply collapse the bridge structure before even reaching the middle of the span. This created an absurd situation. A tank meant to secure territories physically could not reach most of the places where its protection might be needed. Porsche took it upon himself to solve this problem once again. He designed a special railway platform 26 meters long, mounted on 14 axles. The idea was to distribute the immense weight of the machine over a large area and across many wheel pairs. This reduced the load on any specific section of track and existing railway bridges to an acceptable level. The platform solved the railway problem. However, the tank could not travel exclusively by rail forever. Sooner or later, it would have to unload and move under its own power, including across rivers where ordinary road and tank bridges either did not exist or could not support such a weight. Here, the designers proposed a solution that sounds almost like a scene from an adventure film. The tank was to cross rivers not over a bridge, but along the riverbed. The hull design allowed the machine to submerge to a depth of up to 8 meters, completely disappearing underwater, and drive along the bottom of the river on its tracks until it reached the opposite bank. The crew inside would not suffocate underwater for one simple reason. A special snorkel tube was raised to the surface, through which air was drawn for the crew to breathe and for the engine to run. In itself, the solution was engineering-wise quite ingenious. It did resolve the bridge issue where no other options remained. But let us pause for a second and evaluate the entire picture. A machine protected by 20 centimeters of frontal armor, armed with a gun capable of hitting targets 2 kilometers away, and equipped with an engine of over 1,000 horsepower, had to literally dive underwater and crawl along a riverbed, breathing through a tube, just to reach its deployment site. A tank that was supposed to strike terror into the enemy by its mere appearance spent a significant part of its journey either on a specialized railway platform or underwater, hidden from view. This was hardly the image of invincible might that had been envisioned in the headquarters hall in the spring of '43. However, logistics was far from the only problem about which people preferred to remain silent. There was a man who saw the entire picture, from cost to practical utility, and his words, preserved in memoirs, explain a great deal about this story. Albert Speer held the position of armaments minister, the man responsible for directing the country's limited industrial and raw material resources. From this vantage point, he saw the TIP 205 project quite differently from how it was viewed in the headquarters hall in the spring of '43. Speer understood a very simple thing. It was physically impossible to build a machine weighing over 200 tons in large numbers. Too much steel went into a single unit. The assembly was too complex. The production of each specimen required too much time. This was a piece of technology that could only be created in individual examples, rather than a tank capable of actually influencing the outcome of battles through mass presence on the battlefield. In this opinion, Speer was not alone. Heinz Guderian, the Inspector General of Armored Troops, the man responsible for the actual combat employment of armor, held the same position. Two influential specialists, each in their own field, agreed on one thing: the project did not justify the resources invested in it. Later, reflecting on this period, Speer described the situation quite candidly. According to him, Porsche undertook this venture in an effort to please the leadership, and was ready to continue the work even when the practical utility of the project raised serious doubts among most of the specialists involved. It is worth noting another point that Speer emphasized separately. To confuse potential adversaries and conceal its true scale, the machine was given a deceptively modest name, Maus. It was a name that least associated itself with a 200-ton steel colossus. Yet understanding the problem was not enough. The disagreement of Speer and Guderian existed, but it remained a disagreement on paper and in private conversations, never translating into a decision that could halt production. A logical question arises. If two such influential people saw the pointlessness of the project, why was it not stopped? Why did resources continue to be allocated to a machine that the armaments experts themselves considered a dead end? The answer to this question lies not in the field of engineering, but in the realm of human ambition. To understand the mechanism that drove the project forward despite sensible objections, we need to introduce another figure, a man for whom this tank represented not territorial defense, but something far more personal. Speer had a deputy named Karl Otto Sauer. His attitude toward the project was based on a completely different logic than that of the minister himself. Sauer was interested not so much in the outcome of the project as in his own position. He hoped in the long run to take the seat of his immediate superior, and to do this, he needed to secure the favor of those who made decisions at the very top. Supporting an ambitious, spectacular, and impressive project was the perfect tool for this. Unlike the quiet skeptics who understood the pointlessness of the venture but did not dare to object out loud, Sauer acted in the exact opposite manner. He enthusiastically spoke to the leadership about the future of super heavy tanks, using tones that fueled the already considerable interest in giant machinery, rather than cautious, measured phrasing. Here, the story takes a turn that would be difficult to invent even in fiction. Inspired by these conversations, the person who made the final decisions on the project began to dream of an even more grandiose machine. This was when the name of a future hypothetical tank was first spoken, the Landkreuzer P-1000 Ratte, which can be translated as the land cruiser Ratte. The declared mass of this machine was 1,500 tons. 1,500. This is not a typo, an exaggeration, or a fictional license for dramatic effect. It was a real figure, seriously discussed at a meeting where the future of German armored vehicles was being debated. For comparison, this is 7 times heavier than the already described 207-ton tank, which itself could not fit on any existing bridge. Naturally, practical questions immediately arose for the project. The main one was how to transport a machine weighing 1,500 tons to its place of deployment when 207 tons already required a special railway platform and crossing rivers along the bottom. The answer to this question, though logical from an engineering standpoint, was just as detached from reality. The machine was planned to be delivered to the front in parts on separate platforms and assembled on-site in specially equipped field workshops, as if it were a prefabricated house rather than a combat vehicle. The idea remained on paper. Yet the very fact that such a project was seriously discussed says a lot about the atmosphere in which decisions on military hardware were made during this period. An atmosphere where the loud enthusiasm of a single careerist outweighed the sober calculations of a whole group of experienced specialists. However, the absurdity reached its peak not at this meeting. To hear a truly sobering argument against the entire concept of super heavy tanks, it took a man who looked at these machines not from a headquarters office, but from the front line with his own eyes. Speer decided to try one last argument, which he hoped would prove more convincing than any figures or calculations. To one of the meetings on super heavy tanks, he specifically invited a colonel from a panzer division, an officer who had recently returned from the front and possessed the most practical combat experience possible. This man had not seen the hardware on blueprints or in the form of wooden mock-ups. He had seen how tanks burn, break down, get stuck, and get penetrated on real terrain. His speech was short but precise. The colonel informed those gathered of one thing that did not usually appear in engineering calculations. A single hit from an anti-tank shell into the engine compartment was capable of igniting the vehicle's fuel. Given the volume of the fuel tanks required for an engine of over 1,000 horsepower, this meant the virtually guaranteed loss of the entire combat vehicle, regardless of the thickness of the armor on its other parts. In other words, this wall of steel 20 centimeters thick on the front of the hull meant nothing if a shell found the single vulnerable point from the side or rear where the engine was located. The argument was so simple and practical that it was difficult to refute with theoretical calculations about armor thickness. The reaction to it, judging by surviving accounts, was noticeable. The decision-maker looked clearly taken aback by this revelation. Yet being taken aback is not the same as canceling a project. Instead of reconsidering the very concept of the super heavy tank, a solution was proposed in the spirit of the entire project. Not to simplify the machine, but to complicate it even further. The idea was floated to equip such tanks with additional machine guns, controlled remotely from inside the hull, capable of firing in all directions without the gunner needing to expose themselves. From a historical perspective, the idea was, surprisingly, quite progressive. Today, remotely controlled machine gun mounts are a standard feature on many modern combat vehicles worldwide. However, in the mid-1940s, implementing this idea in a real, reliably functioning form was a task on the verge of science fiction. Thus, a practical argument from the front line, which should have stopped in a logical project, ultimately only added another layer of technical ambition to it. Despite the honest warning of the frontline officer, the development could not be stopped. It remained to be seen what this whole story would eventually turn into when the blueprints and meetings finally became finished metal. The first running prototype of the tank was assembled only at the end of 1944, almost 2 years after the wooden mock-up was approved in the headquarters hall. By this point, the state of affairs in the country had changed radically. Industry was experiencing an acute shortage of raw materials. Production capacities were increasingly redirected toward hardware that could be manufactured quickly and in large quantities. It was at this precise moment that the assembly of a machine that could only be built individually from the start was being completed. In total, during the work on the project, 4 prototypes of the Type 205 were constructed. Not a series of hundreds of machines that had been dreamed of in the headquarters hall in the spring of '43, but 4 units. None of these 4 machines was ever used for its intended purpose. Not one went into position against a real enemy. The tank that was supposed to turn the tide of battle by its appearance alone spent its entire life cycle on testing grounds, in trials, and on blueprints. To appreciate the scale of the resources spent, a comparison of cost is useful. One specimen of this super heavy tank cost the production roughly the same amount as 7 specimens of the Königstiger, the very King Tiger we compared by weight at the beginning of our analysis. 7 fully functional combat vehicles, each of which was actually used at the front and proved its effectiveness, versus 1 experimental machine that never left the boundaries of the testing ground. There is a bitter detail in this story that serves as a better conclusion than any summary. Sharing his expectations at an early stage, the project head once remarked that if he had 100 of these tanks, he would certainly be able to deal with a serious enemy in one of the directions. 100 tanks. In reality, they built 4. None of these 4 ever fired a single shot at the target for which this entire multi-billion-dollar enterprise, by today's standards, was conceived. The machine for which the objections of an entire staff of specialists were dismissed, for which raw materials were allocated at a moment of their acute shortage, and for which engineers designed a separate railway platform and a deep weighting system, ultimately remained a museum curiosity rather than a combat unit that influenced a single real battle. Today, from this entire story and the 4 built prototypes, what remains is not 4 machines. Something far more modest in number has survived, and this final link in the story needs to be examined to truly understand the price of the entire project. Of the 4 built prototypes, not one has survived to this day in its original pristine form. However, one specimen did survive, and its story deserves separate attention. The tank preserved today is technically neither the first nor the second prototype in its pure form. It is an assembled machine, a hull from one prototype and a turret from another, combined after the end of hostilities in Europe. In essence, the only surviving Maus is a hybrid assembled from parts of 2 different machines that were not originally intended for each other. Today, this specimen is located in the Military Historical Museum in Kubinka, near Moscow, where any visitor can see it. It stands there quietly, without movement, which is quite symbolic, considering the maximum speed of 20 kilometers per hour that this machine was capable of developing even when it was fully functional. Stepping back a bit and looking at the entire story as a whole, a rather simple yet instructive picture emerges. Several influential people who understood the complete pointlessness of the venture preferred to remain silent rather than enter into conflict. One designer regularly backed the project with fictitious data about non-existent enemy developments. One ambitious official saw the giant tank not as a weapon, but as a stepping stone for his own career. Even the honest warning of a frontline officer about the vehicle's actual vulnerability did not stop the project, but only added another layer of unrealizable technical ideas to it. As a result of this chain of decisions, a machine was born that technically surpassed almost everything built before it in terms of armor thickness, gun power, and engine size. At the same time, it turned out to be virtually useless from a practical standpoint, too heavy for bridges, too slow for maneuver, and too expensive for mass production. The history of this tank is not a story of failed engineering. The engineers actually handled their task in accordance with the conditions set before them. It is a story of what happens when the ambitions of some people and the reluctance of others to object out loud come together, directing colossal resources in a direction opposite to common sense. The 4 built prototypes proved one simple thing: quantity of steel, power, and armor thickness do not always translate into quality of result. If one loses a sense of proportion in this pursuit, they can build the heaviest tank in history and simultaneously one of the most useless.